Okay, well, it's a pleasure to be here at the Institute this term, and thank you very much for the invitation to speak. What I'm going to be talking about today is mostly joint work with Baiying Liu. And I want to start with some motivation that comes from an old work of Gaudamont and Jacquet. All right, so for me, F is always going to be a number field. AF is its ring of Adels. And if I give myself a Schwartz function on the space of n by n matrices, so this is just the usual Schwartz space at the infinite places, tensor the space of compactly supported and smooth functions at the finite places, then if I give myself one more piece of data, psi, an additive character, then I can define a Fourier transform the usual way. So I can define f hat of gamma to be the integral of f of x psi trace of gamma transpose x dx. All right, and you want to normalize the Haar measures here so that they're self-dual in an appropriate sense. And then you have a Poisson summation formula. Which is the sum over gamma in GL n of f is equal to the sum over gamma in GL n of f hat of gamma. Okay, so right. So let me just highlight this. So this is we have a Poisson summation formula, and then we have one other important property, which is an equivariance property. So this is that if I let LH f of x equal f of what I want, h inverse x, then the Fourier transform satisfies LH f hat of x equals determinant of h to the nth L of h negative transpose f of x. Okay, so you have this summation formula and you have this equivariance property, which is, and here, of course, h is going to be something in GLN. All right. And so these two things together actually give you the functional equation and meromorphic continuation of Ls pi via essentially the same argument that Tate used to deal with the case where n is equal to 1. And so you just integrate a Cuss form against both sides of this equation, and then you get this functional equation. So quite a bit later, okay, Braverman and Kazhdan conjectured that if you give any representation of the L group of any reductive group, so then we should have a corresponding Poisson summation formula, which implies the analytic properties of Ls pi r. Okay, so the whole picture should generalize. Okay, so right. Now, of course, the only cases where we have a full understanding of this conjecture are cases where we already know the L function for some other reason. Maybe cases like the standard L functions of classical groups. Go is the relationship between BK and Langland's beyond endoscopy idea. The point of, basically the point of view here was that you could try to use the trace formula to prove the functional equations of L functions by inputting Fourier transforms that you could construct using something like what Braverman and Kazhdan were saying. But finally, the thing that I sort of want to, for the first part of this talk that I want to talk about is something that actually came about a little bit earlier than what Cho put forth, which is that Sacclaridis says that there should be a similar picture for any spherical variety. So in this semester, we've been talking about locally symmetric spaces, and so spherical varieties are playing a key role. And the point of departure here is that this, the point of departure for Ngo is that this GLNF is a monoid. It has a multiplication, and it's in fact a reductive monoid with unit group equal to GLN. And Sacclaridis says, well, you don't really need the monoid structure. Really what you need is a spherical variety. You need G embedding inside this thing, and you need some sort of compactification of it. And I guess what I should say is any affine spherical variety, to be completely accurate about that. So what I'd like to do today, and just, this has come up a lot this term, but just to recall, spherical variety just means open Borel orbit. But so what I'd like to do today is indicate what Bayang and I have done, which is that we prove Sacclaridis's conjecture in a very special case. All right, and it's the first case that is not a generalized flag variety. So what I mean by this is it's not something that looks like G mod the derived group of some parabolic. Okay, and hopefully I'd really like to at the end get to say something about how you might actually use this to study L functions. But first I want to get through the proof of this, which is actually, once you set it up right, the proof is, I can essentially give the full proof. So here's the setup. So a summation formula. All right, and this is, so what I'm going to give myself is Qi Vi. This is a triple of quadratic spaces. So these are vector spaces Vi. This is a non-degenerate quadratic form on it for each I. And I'm going to assume that the dimensions Vi equals D I is even for a technical reason. And I'm just going to use R for an F algebra. So when I look at affine schemes, I can write down what their points are. So I'll let Y of R be the set C1, C2, C3 in V of R, where this V is V1 direct sum V2 direct sum V3, such that Q1 C1 equals 2 of C2 equals Q3 of C3. Okay, so this is the subscheme that's cut out by saying that all three quadratic forms are equal. So it's an intersection of two quadratic forms. And so this is naturally a homogeneous space. So let me write that down in a little bit more detail. So if I let HI be the general, the similitude group of the QI, all right, then if I let H inside the product of these three things be the subgroup on which the similitudes are equal. So each one of these groups comes equipped with a similitude norm to GM, and I take H to be the subgroup on which each of those similitude norms are equal, then this thing naturally acts on this scheme Y, all right? And it acts with open orbit, Zariski open orbit. And so we're sort of in the setting of Janus's conjecture here, because it turns out that this is spherical. So what Liu and I do, and I define for each V a Schwartz space S of Y FV. It's contained inside the space of smooth, or sorry, the space of smooth functions on the smooth locus of FV. Okay, and a Fourier transform that I'll denote by Fy that goes from the Schwartz space to itself. Okay, so I'm going to keep, so I have this, again, I have this left action that you see at the very top there. And I can ask for what is the, I mean, it's not the general linear group anymore, it's this product of similitude groups. And so then the natural question is, what's the equivariance property with respect to this Fourier transform? And so you can write that down. So the equivariance property is that Fy following LH is the, it looks very similar, it's kind of nice. So you have, this is the similitude norm of H. You raise it to the di over 2 power, where di is the dimension of this vector space. And then the analog of the analog of taking the conjugate or transpose inverse is H over the similitude factor. So this is sort of like taking a dual in one of these orthogonal groups. Okay. All right. Okay, so this is the local picture, and you have to put this together into a global picture. So we're going to prove something that's a summation formula that we need to be working adelically. So what's if I'm going to do that for you? So what's the dumb guess, right, as to what? So if you're going to define an adelic Schwartz space, right? Going to the first ways we think about these things. So what should I define this to be? I should define this to be a restricted direct product of the local things. So usually in the theory, the restricted direct product, I mean, we don't even think about this prime, right? Because it's sort of, well, obviously, what are you going to put at all places? You're going to put the characteristic function of the integral points, right? In this case, you can't. And this is one of the insights that goes back to Braverman-Kazhdan, has been developed by Cho and by Janus, is that the singularities of the space force you to not put that. I mean, because this is a singular space, you can't put that as the basic function. So what is the basic function in this case? I mean, I'll write another expression for it, but I can write it down explicitly. I mean, it has to be something that's invariant under the Fourier transform, for one. So j equals 0 to infinity of some integral. And it looks like a mess, but I'll sort of say what this means. So this is a uniformizer to A3 times the characteristic function of the integral points, C over var pi 2j A chi bar. And maybe it's foolish to write this down, but sort of wanted to say that this is a concrete thing. And then this integral here is over everything such that A1 inverse A2, A3, and all the permutations of this A3 inverse A1, A3, and A3 inverse A1, A2 are all integral. Okay, so I mean, this looks like sort of a mess. Let me say that this is a character that's attached to the quadratic form. If the quadratic forms are all split, then it's equal to 1. One thing that you should think of is that this really wants to be the characteristic function of the integral points, right? So if this thing has the property that in each vi, it's a unit in some vector, right? Then all the ai's go away, and this is just the integral, right? So this thing will be bigger if or you'll have more structure if this thing is very divisible by p in each of the factors. Okay? All right. All right, so then we have this, so we can define the short space. These are the basic functions outside of finitely many points. And then, so the theorem should be sort of no surprise at this point. The sum over xi in y of f of xi is equal to sum over xi in y of f of the Fourier transform of f of xi, where I have to put under assumptions on f, right? So you have to put in assumptions that basically kill boundary terms in this, but okay, let me not get into that. Okay.
Did you say the basic function was self-dual?
Yes.
Is that
Right?
clear, or?
No. It's not even clear what, I mean, from a different perspective, I mean, I'll give you another formula for the basic function, and from that perspective, it will be clear. But from this perspective, it's far, I mean, I haven't told you what the Fourier transform is either, so, right.
Is this always smaller than 1, the value? The basic function.
The basic function, so,
Bounded?
yes, so it will be, right. It is going to be, no, I mean, it can blow up. So this is what happens, and I'm going to talk about this in a moment. So what happens, what does the short space look like? So this short space, so this functions in here are smooth, right? What does the short space looks like? If you go out to infinity in a certain sense, and I'll say precisely what that means, then it will be, at a non-Archimedean place, will be compactly supported. As you go to 0, it'll be have polynomial growth. So you actually, when you're writing down this formula, right, you're actually using the fact that, I mean, the thing blows up. It's nasty as you go to 0, but the growth that happens as you go to 0 at the p-adic places is killed by the fact that, well, if you're divisible by a lot of primes, right, then you have to be big at the infinite place. So it's subtle, right? I mean, it's not, it's...
Assumptions on f aren't at 0?
The assumptions on f are, yeah, I'm not going to assume, yeah, I'm going to kill 0, right? Is one of the assumptions. So, all right. So, all right. So let me explain how we do this, but I mean, maybe I can say just in a couple words, so you can sort of see see where we're going. So, in one sentence, I mean, how do you prove? Plug 3 theta functions into Garrett's integral representation. Okay, and if that doesn't mean anything to you, that's fine, because I'll say it in a different way, right? But I mean, that's for the people who sort of know about the integral representation for the triple product, then this is sort of the crux of the proof. But I mean, all right.
You don't have any dependency. You can't give a proof which is directly avoiding.
No, I'm not. I can't give it directly. Everything comes back to that integral representation. So
What would be the ambient group for which?
just yeah, I'll tell you when it gets. So it's SP6. It's SP6. But just
These are dimensions.
yeah, just okay. Let me wait till I get to it. But yeah. So if you zone out or something, you can try to figure out how to write this. So it's not strictly necessary. You can get by looking at Eisenstein series, but maybe because of this perspective, it's useful to talk about summation formula for Braverman-Kazhdan spaces. So these are the generalized flag manifolds I mentioned. So if I take the Siegel parabolic in SP2n, and I want to normalize things, so I'm going to use IN to define the form. And then my Siegel parabolic is going to look like this. IX, IN, where A is in GL and R, and X is equal to the transpose of X. Okay. All right. So then I'm going to look at a flag manifold. Or it's not quite a flag manifold. It's a GM torsor over a flag manifold that improve a summation formula. Well, Braverman-Kazhdan proved a summation formula for this. Okay, so I'm going to let X be this space. So this is the derived group of P. So this is just a GM torsor over the flag manifold SP2n mod P. And what Braverman-Kazhdan did, Braverman-Kazhdan defined for all V short space that I'll just call SBK of X FV, which is inside X of FV. Okay. All right. And a Fourier transform. From this space to itself. Okay. And they also defined in this context basic functions. So let me just write down, so basic functions. So when n is equal to 3, which is the case I'm going to be using, the basic function looks like sum equals 0 to infinity, sum b1 b equals 0 to infinity, q to the 2b times 1. A plus 2b. All right, where 1 sub c is the characteristic function of this set. Okay. So they defined a Fourier transform, and I don't really want to get into the definition of this. All I want to say is that this thing covers Q. Here, this is the residue field, cardinality of the residue field. I just wanted to say that the basic function is pretty, I mean, it's a pretty concrete object. It wants to just be the characteristic function of the integral points again. what is this, right? What is this Fourier transform? This covers the intertwining operator that is sort of implicit in this. So if I take a Mellin transform along the center of A and push down to this flag space, then I get a principal series representation. And then you have the standard intertwining operator that goes from that to its dual. And what Braverman-Kazhdan do is they isolate a normalization of that, which is not the same as the canonical normalization, but is set up so that you get this duality. Okay? It's the same normalization that comes into the treatment of the standard L functions. So I think, Erez, you had a paper where you you basically redo a lot of what PS and Gelbart, or PS and Rallis do in this context. So anyway, this is this Fourier transform. And they also prove a summation formula in this context. But the proof of the summation formula in some sense is a bit, well, it's sort of just a rephrasing of something from the theory of Eisenstein series. It's just the statement that F gamma is equal to the sum over X of F of okay. But all this is this is essentially taking the functional equation of a degenerate Siegel-Eisenstein series and pulling it up. Right, so there's, I mean, that's all there is in terms of content for this. All right. So one remark to make about this, though, is that if you let PL be the Plücker embedding from this space into GA to the 2n, right? So all I'm doing is, I mean, if you think about it in terms of matrices, I'm taking the nth.
What is the role of the basic function in the Poisson summation? Is it that F must somehow respect the basic function it almost would?
Yes. F has to send the basic function to itself. So in terms of the Eisenstein series, so when you're using, when you're doing the standard L functions for classical groups, then there's a factor that you have to worry about in order to kill the trivial poles of the Eisenstein series. And that factor is essentially exactly what this is constructed to do. And Braverman-Kazhdan gave a nice...
The condition on F in the Poisson summation formula involves the basic function.
Yeah, right. So the F has...
All places or
Yeah, you have to have F be in this Schwartz BK
okay.
of X.
Right.
Yeah. Right. And it's interesting because the Eisenstein series itself doesn't exactly see that, because it cancels this gamma factor comes in as actually, turns out when you take the product over all places, it's 1. What I was saying in terms of this Plücker embedding is that as Plücker of X goes to infinity, F of X is rapidly decreasing.
Can you tell what the Plücker embedding?
So all I mean is that if I take, so this is this generalized flag manifold, and I'm just taking the last n rows of the matrix and taking their wedge product into here. And so, I mean, in this case, that's what that becomes. But the point is that this realizes this space X is a quasi-affine space. And there's a natural metric on this. Right, you can take any k-invariant metric that you want on. I mean, just take the max of the entries, p-adic absolute value, and so as the Plücker embedding goes off to infinity, the function is rapidly decreasing, and as the Plücker goes to 0, f of x has at worst polynomial growth. And Braverman-Kazhdan actually didn't sort of assume these things, so Bayang and I went back and proved these analytic results that you need if you want to apply their work. Okay, so now we get to the proof of the summation formula. Okay, so now Regerum, I can tell you what the groups are and so on. So so I'm going to let G be SL2 cubed, which I'm going to put inside SP6. And this is sort of the, I mean, the matrices here look something like, I don't want to write it down, but like, you see what I'm, so this will be one copy of SL2, and this will be the other copy of SL2. And then the important point here is that G acts with open orbit on X, right? Which is, again, this is this generalized flag manifold. And for better or worse, this is, if you tried to generalize this to higher rank, that becomes false very quickly. But, OK. So if you you can choose gamma naught in X of F, a representative for this open orbit. So choose, and then such that the stabilizer, G gamma naught, is equal to the set of matrices 1, T1, 1, T2, 1, T1, minus T1, minus T2, 1, where T1 and T2 are saying whatever, if I'm looking at R points, say. OK, so the stabilizer of this thing, and this is already, I mean, it's essentially in Garrett and then written in something that, it was also written down by Piatetsky, Shapiro, and Rallis in the adelic setting. So the point is that the stabilizer of this point is this unipotent subgroup, all right? So what happens when I take this and I plug in 3 theta functions into the picture? So to back up for a minute, so we have our VIs and QIs, right? So these are quadratic spaces, and this gives us a Weil representation, which is rho GAF acting on the short space of AF. OK. All right. And now so what I'm going to do for you is I'm going to define what the short space is, both adelically and locally. And it has the following odd definition. So I give myself a function that's in the Braverman-Kazhdan space, and a function that's in the usual short space on the vector space. All right. Now, if I give myself a point in the smooth locus, then I'm going to define an integral I f1 f2 of xi is equal to the integral over G gamma naught AF G AF of f1 gamma naught G rho G f2 C dg. Okay, so this again is the stabilizer of that point in the open orbit. And what I'm going to do now is I'm just going to define my short space to be the space of all these functions. Okay. So let's see what was. All right. So the short space is then equal to space of I, F1, F2, or F1 and F2 is in the Braverman-Kazhdan short space across Okay. And then how should I define my Fourier transform? So this is, I will define my Fourier transform by just saying what it does in the first factor. Okay. All right. So that's the Fourier transform. So it's just completely induced by the corresponding Fourier transform of the first factor. All right. Now, from this definition, it's not clear that the Fourier transform is well defined. And Giannis at one point tried to sketch to me an argument of why it should be well defined using locally. Sort of the best that I could do is using a global argument to deduce that the thing is well defined. So essentially, you know I'm going to write down a Poisson summation formula for you, and then you use some sort of global to local to get this thing to be well defined at any place. Okay. So now let me prove of the summation formula. Okay, but before I do that, to get back to your point, Farrell, so you asked me about, well, why is it self-dual, right? I mean, from this definition, it's sort of stupid that it's self-dual, because you know that the original test function here, if you put in the basic function, then it's self-dual. Okay. So, all right. So here's the proof of the summation formula. So if I give myself an F2 that's a Schwartz function on this vector space, then I get a theta function. So this is the sum over all C and V of F of rho G F of C. All right, in the usual manner. So now I'm going to use BK's summation formula. So now by the BK summation formula, which is really just the functional equation of Eisenstein series. So I mean, I don't know of any simpler proof other than Roberts of these things. Although maybe for Siegel you can do. I mean, maybe there's a way to make it easier. But so you have that the integral over the adelic quotient of G. Bless you. dg, well, this is equal to the integral over g of sum over gamma in x of f theta f2 g dg. And at this point, and you just unfold. And the beautiful thing is that, well, I mean, what's going to happen when you unfold this formula? So you're going to pick up, so when you unfold this formula, you're going to have this integral over this stabilizer, right? And the integral over the stabilizer is precisely going to pick out the condition that the three quadratic forms are equal. That's just, I mean, it's just built out. I mean, it's stares at your face in terms of the definition of the Weil representation. You know how the upper unipotent acts. Okay, so unfolding, you get that the sum over C in y of f of I f1 f2 C is the sum over C in y of f of I of fbk of f1 f2 C. Okay. And of course, to make all this rigorous, we make some assumptions on f to kill a bunch of boundary terms that, you know, should be removed, but at this point it's probably not the right thing to focus on. Okay. So now I want to talk about what's the relationship of this thing to L functions. Right. So let me give a naive attempt at an application. I'll show you what goes wrong. So. Okay, so remember we had this subgroup of the product of similitude groups. All right, so this is the subgroup. So these are the similitude groups of each of the quadratic spaces, and this is the subgroup on which the three similitude factors are all the same. Okay, so now the summation for, let's give ourselves pi a cuspidal automorphic representation of HAF, and give myself a vector in it, smooth. So if I just follow Braverman-Kazhdan's lead, then I get a functional equation for the following gadget. So if I take the integral over h of sum over c in y of f, phi h f h inverse c lambda h to the s dh, then, well, the first observation is that by, oh, I should really put this outside, but OK. By the summation formula, you get a functional equation for this, right? So it's going to relate this to negative s plus something, all right? Now, so what do? You say, OK, great, so let's unfold. You get the integral h af of f h inverse c naught lambda h s integral over the stabilizer of a generic point of lambda of phi of h dh. All right, and you feel really good, right? But then you realize this is equal to 0. Because this is going to be, as soon as the dimensions get big enough. So this is going to be a product of orthogonal groups of, let's say rank 1. No, rank is not right. No, rank will be OK, 1 less for in each of the factors. So there's this vanishing result of Ash, Ginsburg, and Rallis that tells you that for Cuss forms this is going to be 0. OK, so then you run into this problem. So what can you do? Well, so one way that you can proceed, and this is where the talk gets into the speculation. So right. So and the camera people are gone, except for the one at the IAS that actually, somebody.
You can control that still.
Yeah. So no. I mean, you can put it up. That's so. Yeah. Yeah. So now you can start, making comments, I guess. So all right. So what should one try to do? Well, there's nothing saying that we have to. So we're taking H and we're taking sort of a standard representation of it. There's nothing saying that we can't enrich that standard representation by taking some other space on which H acts. All right. And because I'm most comfortable just with the integral representations of general linear group L functions, I'm going to sort of switch focus a little bit. So I'm going to talk about enrichments of the summation formula. All right. And the moral of it is going to be, well, if this thing is 0, then multiply it by some Eisenstein series and make it non-zero. All right. So how do we do? And of course, life isn't that simple, but I mean, that's a starting point. So I'm going to change notation. So now G is going to be GL3 3 times. And I'm just going to talk about sort of the simplest setting. I'm going to take VI to be GA cubed. And there's an action of GM cross G on V which is, again, the sum of VI's. So what I'm doing is I'm viewing this, instead of looking at the orthogonal group, I'm looking at a split unitary group inside of it. So what do? You say, I'll take lambda comma g, x, y is equal to lambda inverse g negative transpose x gy. Okay, so then this preserves the subscheme y if we take qi of x, y to just be the dot product of the two factors. Okay. All right. So then now if I do this and I integrate, I'm going to get 0, just like before. So I have to somehow enrich my space y. So what I'm going to do is, I mean, there's a couple different ways you can think about this, but I mean, maybe the thing that looks the most familiar is if I enrich it using an Eisenstein series. So let's give myself a quasi-character C times a Schwartz function in the usual sense on 3 copies. I'm going to let E0 be equal to the vector that's 0, 0, 1, 0, 0, 1, 0, 0, 1. So everything has to sort of be 3 copies here. I have a standard, I mean, in one of Jacques Hay's papers, he calls these Gaudemont sections. So this is a section of a particular induced representation, sort of trivial induced representation. And I'm going to form the associated Eisenstein series, which is the sum over gamma in P of F, G of F, of, phi chi gamma G. Okay. So this is the same Eisenstein series that shows up in Rankin-Selberg theory on GLN, for example. Okay. And so what's the replacement? So this thing here, that was somewhat disappointing because it just gave you 0. But the replacement in this setting for dagger should be the following. So I'm going to give myself pi equals pi 1 tensor pi 2 tensor pi 3. This is an automorphic representation of GL3 3AF. I'm going to give myself a vector in its space, and I want to consider the vector, or the integral, which is the integral over GM cross phi G EG phi chi sum over C and YF F of lambda G inverse D times lambda DJ. Okay? So all I'm doing is I'm taking my original attempt, which is the same thing without this, right, and enriching it with this Eisenstein series. Okay. So this, again, has a functional equation. So if pi has trivial central character, it has a functional equation I phi fs is I of phi s in this case. All right, so now you're in business. So now the question is, okay, well, first off, is this 0, right? And the answer to that is that, I mean, it doesn't, so is no. What happens when, I mean, maybe I can say something about what happens when you unfold this, but when you unfold this, you again get a unique orbit. The thing that makes it difficult is that the corresponding stabilizer is not a spherical subgroup. Okay? So usually in this theory, you want to unfold to a spherical subgroup because then you have formulae that tell you what that linear functional is. However, even in this case where you don't unfold to a spherical subgroup, you unfold to something that can be easily related to a spherical subgroup. So what ends up happening is that this expands not to sort of something on one orbit, but it expands to something that's a direct integral over a torus, over the characters of a torus. And that's the thing that you get out of this functional equation. And so the question is, like, write that down explicitly and figure out what's actually going on with it. I mean, maybe, you know, the naive hope is that this is, I mean, maybe it's, I don't know if it's naive or not. It's the hope. So the hope is that this is related to, the L function LS product. I mean, so this is just, you know, maybe pipe dream, but to something that looks like this, right? So I have to, so from the shape of the functional equation, I mean, what's happening, this phi is not changing, right? And this is somehow, I mean, you're getting this out of something that has to do with a similitude group. So somehow you're not going to separate pi and pi dual except up to some character, right? So that should be built into whatever L value you're getting out of this. However, in the summation formula, all three factors are linked, and they're linked in a non-trivial way. So, I mean, this somehow seems like the most natural guess, but it's just a guess. And, you know, I mean, actually, I'm going to meet with Giannis on Friday to try to get him to explain his paper on spherical functions to me, because I don't know what colors are or of spherical varieties or anything, so I got to figure that out. I think maybe this is a good.
Without it's always 0.
It's always 0. Well, except for cases where you already know the triple product. I mean, so if you put in GL2 cross GL2 cross GL2, then it's not 0.
So that would mean the L function has always 0? It's 0 of this Einstein series?
Right, but right, but it's not the Eisenstein series that's powering the functional equation. It's not this chi, right? Right. That's a good observation. So, I mean, in principle, this thing actually has 8 functional equations, right? Because you can also take a functional equation in each of these. And so I guess that's one consistency check that one should do, that I should do. That
There might be more factors.
yeah. So I mean, that's the right. So I think I'll stop there.
Do you have any? Have you ever taken this Saito-Shintani, then you have a pre-homogeneous vector space, you have Poisson summation, ordinary Poisson summation.
Yes.
The singular set you have to remove is quite complicated.
Yes.
That's understood. And when you apply Poisson sum, and in their theory, you get not L functions in the way we call them L functions, but you get these series which have a functional equation which are decorated by class number things. But I wonder if there's some. Did Braverman-Kazhdan discuss that case? Because that's the simplest case.
So, I mean, the person who's spent the most time thinking about that is Wenwei Li. About pre-homogeneous vector spaces.
And could they connect it up with this kind of?
So the point really is these stabilizers, right? But this is sort of maybe one, I mean, how do you write, you can write this in terms of those, in terms of that. This is a special case. So, I mean, the case you're looking at is V cross V duo cross V. That's a prehomogeneous vector space. And this is that. So you take a copy of GM, have it act on this factor on the other side, and then you have your group G act diagonally on all of these, and you have a scalar vector that acts on this one factor. So actually, after doing this and figuring something out like this, I looked through those tables, right, to find something where the relative invariant was quadratic, right? And this appeared to be the simplest example of that. And you can generally, I mean, so I should mention that this sort of construction, I mean, it immediately works, I mean, you can blow up the rank. There's no constraint on the rank. What you do is you take this and you fatten it up by some other number of factors, like m minus 2, where you're working with GL m, right? And then you have a GL, you have, instead of the GM acting on the other side, you have a GL m minus 2 acting on this factor, right? So you think about this as like m by m minus 2 matrices, okay? But that's I mean, this computation of understanding what this means is interesting from that perspective as well, because even if it doesn't give you anything in this, it's sort of letting one know what those things mean in this case, which should, in principle, not be as complicated as those Shintani zeta functions can get in general.
So if you start with the triple product of GL2,
yeah,
then you can recover the L function, right?
Right, but I mean, you sort of are using.
So, but is this the integral essentially the same as the previous Riemann integral? Or is it?
Yeah, yeah. I mean, Aaron pointed this out to me that if you look at this basic function that I wrote down, you can fairly quickly relate it to that, right? So I mean, I mean, we're really using that integral representation. Another remark is anytime you have an SL2 that's in your favorite integral representation, you can play the same game. So one case that I think would be quite nice is, which is related to what I'm doing here, right? So you take a DN type, you put a GLN, and you put an SL2 and an SL2, and then your summation formula is going to be weighted by some automorphic representation on GLN something. And this is very attractive because if you can get this sort of thing to work, right, you're going to want to try to apply converse theory and prove that these things are automorphic, right? I mean, that's sort of the end game if it ever gets that far, right? And having an integral representation that looks like this seems like more manageable for that. And in fact, A.L. Kaplan in his thesis worked this out for this an integral representation for this Langland-Shahidi. The Langland-Shahidi L function that corresponds to this, crossed out Dingen diagram.
He's going backwards like you, but he's using is he a student of Shahidi?
No. This A.L. Kaplan just. I don't know what the motivation was.
He himself worked out some of these Braverman-Kazhdan cases.
Right.
Using
right.
the cases that he encountered.
Yeah. So I mean there are lots of points that. I mean, so it's if you have to look at this stuff, I recommend looking at Shahidi's work on it, and it clarifies some things. So
But the hope of this L function, even after you sort of multiply it out, the triple product factors are outside the Langland-Shahidi list, looks like.
yeah, that's the whole point.
If you have three orthogonal groups.
Yeah, that's the whole point. That's the whole point, is to bust out of it. Well, I mean, that's, I mean, yeah, like I said, I have to tell you why I'm doing this for like the dream, right? But I mean, I've dreamed other things before, and it has not worked out. So, I don't know, but I mean, this is the best thing that I can come up with at the time. So.
Do you have any other questions? Well, if not, let's thank Jayce again.